various organizations like DRDO, DST, JSPS, SERI, etc. He has successfully completed the Indo-UK Consortium project, UKRI, which was a major multi-institutional project in the domain of microstructured optical fibers as a coordinator from MNIT. He has been a host scientist for visiting fellows under C.V. Raman International Fellowship for African Researchers, administered by the Ministry of Science and Technology, Government of India, and a host scientist for visiting researcher under RTF-DCF Fellowship Scheme for Scientists of Developing Countries, administered by NAM and Science and Technology Center, Government of India. He has been conferred a Career Award for Young Teachers by the AICT New Delhi and Derek Craig Prize of University of Nottingham for Excellence in Research. He has published more than 180 research papers in reputed journals and conferences and a number of book chapters. He has supervised 10 PhDs till date and currently more than 8 are underway. He is on the panel of distinguished traveler lecturer program of reputed international societies like ISPI USA, OSA USA, under which he has delivered many invited talks across the globe on recent advances in photonics and related technologies. He has extensively traveled to countries like Austria, Bolivia, Canada, China, Czech, Denmark, Egypt, France, Hong Kong, Indonesia, Japan, Netherlands, Poland, Singapore, Spain, Sweden, Taiwan, Thailand, and so many, to deliver talks, present his research papers, or in a connection with other research academic activities. On the administrative side, he has held various key positions such as Associate Dean Research and Consultancy and Associate Dean International Affairs at MNIT Jaipur. He has also served as Coordinator Campus Networking, Nodal Officer National Knowledge Network, and Coordinator Global Initiative of Academic Research. So now I invite Professor Vijay Janyani sir for his talk that is basically based on the overview of optical communication. So yes, sir.
Yeah, thank you, Dr. Amit.
Welcome, sir.
Yeah, I'm audible?
Yes, sir.
Yeah. Okay. So thank you for giving me this opportunity. And this course is on FDP is on optical communication and its recent advances. So you will hear many interesting talks throughout the program. So this first talk is actually aimed at giving you an overview of what optical communication is, what are the advantages, what are the various devices and various techniques. And then later on in later courses, you will learn about, you will do deep diving into those technologies. So let me start my presentation. I will start sharing my screen. Yeah, is it visible now?
Yes, sir. It is visible.
Okay. Okay, so let me start this presentation, which is Introduction to Optical Communication. Basically, it is fibers, devices, and networks, and their recent developments. So I will be covering some of the basics, and towards the end of this lecture, I will be discussing some of the recent advances and the recent developments in which you can do this research, can take your career into those areas. Now, this is a slide. If you see in this slide, on this axis, it is the year starting from 1995 to a projection to 2025. And this actually, this is the data of US broadband households by nominal data rate. That is the percentage of households. I'm just trying to set up a ground for discussion of optical fibers, why they are required, why they are useful. Now, actually, this data is pertaining to US broadband households, but it applies to more or less any country. Even in India, a lot of progress is being made. So here you see that initially you see this red curve, the people, they were having a speed of 1.5 Mbps in their homes somewhere around 2005 or 2007. Then that number started to decrease, and then there was another number, 6 Mbps. The number of households having a data speed of 6 Mbps started to increase. This is the number of households. Then after that actually went down, and then there was 24 Mbps. So similarly, now people are talking of 100 Mbps and above right in their homes. I'm sure many of you must be using broadband in their homes, and 100 Mbps speed is very common nowadays. And I mean, as we go forward, we are looking for even higher speeds. So what is the idea behind showing this slide or this data is that there is something which is actually making all this very high speeds possible, which is making bringing this high speed, high data rate internet to your homes, and that is nothing but the optical fibers. Without optical fiber backbone, all this development and all these achievements are simply not possible. So this graph shows you the evolution of transmission capacity of the optical fibers. Now, just again to give you an idea that what transmission capacity we are talking about. In the previous slide, I said 100 Mbps is coming to your homes. Now here we are talking of something much higher than that. First of all, you see on this axis, the vertical axis, it is the capacity in bits per second. This is, of course, 1 Mbps. That is 1 gigabits per second. That is terabits, and then petabits, and then so on. So basically, we are talking of, when we talk of optical communication, we are talking of very huge bandwidths. I mean, such bandwidths which we have not seen in our lives till now, but they are existing. They are very well there. Terabits, 1 Tbps speed, 1 terabits, you write it as Tbps, terabits per second. These speeds are achievable, although they are not right now available to the households directly in the houses, but they are available in backbone or long haul networks. So you see that how the fiber optics has progressed from 1980 to till today. Basically, you see this line, it is going like this. So the trend is that the capacity in bits per second is increasing somewhat 10 times in every 4 years. This is the trend that we are seeing. There may be ups and downs in this trend because of various reasons, but this is normally the trend. So you see that various things which have made this tremendous development possible are various breakthrough technologies that have taken place during all these years. One of them, of course, is the improved transmission fibers. And this is continuously happening. It is not that initially only it took place. We are continuously having better and better fibers with lower losses, with new operating windows. Then this EDFA, EDFA is the short form for erbium doped fiber amplifier. So it is a type of fiber which is amplifying the signals in the optical domain. Usually, before that, what people used to do is that any optical signal they converted to electrical signal, then they amplified it, and then again they converted this electrical to optical. So now, after the advent of EDFA, now this need is not there, and you can directly convert from optical to optical without any conversion to electrical domain. So that has given a big boost to the speed, high bit data rate available in optical fibers. So that is one big landmark, of course. And of course, before that, 1980, the laser invention of laser, it was the one of the major factors which made the optical fiber communication possible. Then after EDFA, you see WDM was another major landmark. WDM is wavelength division multiplexing. Just like you have TDM and FDM, this WDM is wavelength division multiplexing. It was another landmark which multiplied the capacity of optical fibers manifold. After that, there are many developments taking place. High spectral efficiency coding. There are a lot of modulation formats and coding schemes which are being used, QAM and QPSK and polarization division multiplexing. All these are taking place. So they have really changed the scenario, and I mean, you have a very huge bandwidth available. The latest trend nowadays, which I will discuss towards the end of this presentation in slightly more detail, is the space division multiplexing. That is something which is very recent, and it is expected to give another boost, as you can see, to the network capacity of optical fibers. So what is the optical spectrum basically? This is a complete spectrum, not only the optical, it includes from X-rays to far infrared. So basically you see that this is the visible spectrum. I can hear some noise. Someone mic is on.
All the participants are requested to kindly turn off their mic, please. Participants, please turn off your mics.
Yeah, okay. So see, I mean, this is the visible spectrum, visible part, which spans from 100 nanometer violet to 780 nanometers, that is red. So this includes your complete spectrum, visible spectrum, which you call as WebGR shortly. Then on this side, you have the ultraviolet radiations, and on that side, you have the infrared. Further, you have classification as near infrared, mid infrared, far infrared on this near and far UV. So actually, this optical spectrum is completely represented by this, including visible, ultraviolet, and near infrared mainly. But of course, you are working in mid and far IR now. These are just some fundamentals to get going. Wavelength, you know, usually you represent in 10 raised power minus 9 meters or nanometers, sometimes in also micrometers. So frequency is measured in terahertz, because normally in your RF domain you measure it in megahertz or at the most gigahertz. But here you commonly measure it in terahertz because it has a huge bandwidth capacity. That's the speed of light. These are some of the very common optical fiber communication bands. You give them name as O band, E band, S band, C band, L band, U band. Of course, the C band is the most popular and most common communication band for optical fibers. This is C is the conventional band, and it is actually erbium window. And this C band is from 1530 to 1565 nanometers. The very popular wavelength 1550 nanometers, that actually falls in the C band. Now, if you see this bottom diagram here, it shows you the wavelength versus the transmission loss or the attenuation of the optical fiber, which is basically made of silica. We are mainly talking of silica because silica is the most commonly used fiber in optical communication. So what in this diagram you can see, this attenuation diagram is something like this. Then it is again increasing here, high attenuation in the E band. That's why this E band is not very popular in optical communication. Then again it decreases, and then you have a minimum attenuation somewhere here. So this minimum attenuation, I mean here also and here also, this minimum attenuation usually it is 0.2 dB, 0.2 dB per kilometer. 0.2 dB per kilometer. So that is the lower limit of silica. Here, I mean, silica can give you the minimum loss of 0.2 dB per kilometer, not below that. So this O band, S band, C band, and L band, these are the most commonly used bands. And O band is also sometimes used because of historical reasons, or because it has low dispersion actually, that you will come to know later on, or if you do some in-depth analysis. So these are the popular wavelengths which are used. Now coming on to the system, that is the optical transmission system. Optical transmission system, as you can see, it is represented by broadly by this block diagram. Of this optical transmission system, this optical fiber is only a small part. I mean, small but very important part. So basically, you see on the left hand side of this, you have a transmitter, and this is the transmitter, and you have a driving circuit, a power source, which is either a laser diode or a LED. These are the two most common sources available for optical light. Then you connect, convert this optical signal. This is the electrical signal. You convert it to optical by modulating this laser diode or LED. Then you launch this signal into this optical fiber. Now this optical fiber, it may be very long. It may be many kilometers, maybe 100 or even more than that, 100 kilometers long. So naturally, you will somewhere you will need some amplifiers in between, EDFs. Then on the receiver side, this optical signal is converted back to electrical signal by using a photodiode. So photodiode or photodetector, actually, photodetector is something which converts your light energy into electrical energy. And then again, it is available for the network on this side. So that is the complete fiber optic communication link or communication network. Now, how the evolution of fiber optic communication has taken place, it is interesting to learn briefly about this. This fiber optic communication actually started somewhere in the 1960s. Around that time, the people started to learn and they came to know that yes, optical fiber can be used for transmitting light for communication. And of course, 1960s laser was invented 1960, so that was a big boost for this research. In 1966, this was a major achievement. Charles Cow and Hockam, they, demonstrated that attenuation in optical fibers could be reduced below 20 dB per kilometer. Of course, today we are talking of 0.2 dB, which is much more less than that. But at that time, they demonstrated that that time it was a low attenuation. Before that, it was even higher. And this Charles Cow, actually, he received a Nobel Prize for his pioneering work in optical communication. Awarded to Nobel Prize in Physics in 2009. Recently, not long back, in 2009, 10, 11 years back, he was given the Nobel Prize in Physics for his work in optical communication. So that is the importance of optical communication, how important and how significant it has become. So evolution of fiber optic communication, the first generation, again, this diagram is that attenuation diagram, which I have just shown you on the previous slide. So you see that the first generation was 0.8 micrometer wavelength. It was somewhere here. The attenuation was quite high at that time, at that wavelength. But later on, when the second generation was developed and discovered, around 1980s, then it is at 1.3 micrometer, or you can say 1330 nanometers, because it's very common in optical communication to talk in terms of wavelengths in nanometers and micrometers. So this is the second generation. And the third generation was when people moved to 1.55 micrometer or 1550 nanometers wavelength, where the attenuation was found to be lowest. As I said, it was 0.2 dB per kilometer. And optical amplifiers also were discovered during this time. And then you can say fourth generation also was there in 1996 when WDM systems they came into existence. WDM is actually you can combine many different channels or many different wavelengths and they pass through the same fiber acting as if they were different signals and different channels. So multiplying the capacity of optical fiber communication. Then from WDM as the technology developed, people were able to handle more closely spaced channels here in this using multiplexing. That gave rise to dense wavelength division multiplexing, DWDM. And now, of course, people are talking of ultra DWDM, that is ultra dense wavelength division multiplexing. So this further increased the capacity of optical communication. The present and next generation is we are not talking of only optical fiber from one point to other point, but we are talking of optical networks. And that too, we are now aiming at all optical networks. Although they have not been fully realized till now, research is still going on. That's why I say it is the next generation also. So all optical networks will be those networks in which there will be no electronics involved. Everything will be based on photonics and light. You will have components, you will have devices, everything based on photonics that will give it a very high speed without the need to convert to electrical domain. Then you have specialty fibers now available, photonic crystal fibers and different type of designs. And then there are concurrent developments in photonic components, modulation formats. So every field actually related with this is being yeah, participants,
Participants,
I can see
please,
your noise.
participant, please turn off your mic.
Yeah, so this is what I was saying is that there are development taking place in each and every field, whether it is modulation, whether it is devices, whether it is fibers. So we are now talking of speeds up to terabits per second. Advantages of fiber optic communication, I'm sure those who are familiar with fiber optics, they know the advantages. So I am not spending much time on this because we are already slightly behind schedule. So let me cover it very quickly. The biggest advantage of optical fiber communication is the high information carrying capacity. As I have mentioned, we are talking of terabits per second. So there are plentiful of resources. The silica is made, I mean, it's available in plenty. So you do not have any restraint on the material available. We have a lot of that. The attenuation is very small. As I said, zero point 0.2 or 0.3 dB per kilometer. That is a very small attenuation as compared to your coaxial and other cables. Also, it is more secure and safe. Optical fibers are either made of glass and plastic. These are insulators or dielectrics. These are not metal. So normal problems like electromagnetic interference and short circuiting and these problems are not uh, present in optical fibers. They are immune to RFI, radio frequency interference, just because of the same reason, because they are insulators, not metals. These two reasons are basically because of that. There is no crosstalk. Again, if you are laying two fibers side by side with very small separation between them, I mean, just like a normal copper cable, it will have its magnetic field and it will interfere with the other mutual interference. That is also not present here. Higher security because again, it's not possible to tap the optical fiber. Just like you have a copper cable and you can make a connection out of this, and you can take a parallel connection out of it. So all this current which is going there, you can detect here also. It is not so in case of optical fibers. It is not simple. I'm not saying it is impossible, but it's very, very difficult to take a connection from here and take a parallel path. It's very difficult. Of course, small size and lightweight of optical fibers is very important. Here example is given. Typical optical fiber cable with diameter 125 micrometer and weight 6 kilogram per kilometer. If you take a coaxial cable with the same amount of data carrying capacity, its weight will be this much, 1110 kilogram per kilometer. This is just a rough estimate. Don't take it exactly. But I just want to give you an idea that how lightweight and how small size these fibers can. And then, of course, there is no corrosion. Again, just like metallic. So the working principle or mechanism of optical fiber is total internal reflection. We call it as TIR in brief. So you can see in this diagram and also the animation and at the bottom. Is the animation visible?
Sir, visible, sir.
Yeah, okay. So here you see that you have a light source, and basically it depends on what angle this light source is striking this boundary of core and the cladding. So you know, optical fiber has a core of a slightly higher refractive index and a cladding of a slightly lower refractive index. So this depends very much on the angle at which this ray of light is striking here. And if it is, say, striking at a very small angle measured with respect to the normal, very small angle, then you can see it escapes into the cladding, which is not desirable. But if you launch it at a proper angle, it starts to reflect internally back. Also, there is some refracted signal. But if you talk of total internal reflection, then you see that the waveform is totally reflected, and this is how the light is carried in an optical fiber through hundreds of kilometers of glass fiber. So this animation at the bottom, it says you the same thing, shows you. This angle actually is varying, and you can see that for a larger or a smaller angle, this is escaping here. But if you launch it properly at a proper angle, it is confined within the core. Now it is going into the same core. The basic material, as I said, you use sand, and sometimes now plastic fibers are also commonly used, although their quality and performance is not as good as silica fibers. And then you have various dopants added to increase the refractive index or decrease the refractive index. Because I mentioned that this core is having a slightly higher, Ri is the refractive index. This core is having a slightly higher refractive index, cladding is having a slightly lower refractive index, but of course both are made of the same material, silica. So you add some small amount of dopants into this if you want to increase or if you want to decrease. And this diameter is very small. This is the cross section. This diameter is, if it is a single mode fiber, this diameter is 9 micrometer only. You can imagine how small it is. It's even hardly visible with your naked eyes. 9 micrometer is the diameter of this. If it is a multi-mode fiber, then of course it is slightly more than that. It may be up to 50 micrometer. And this cladding is 125 micrometers. So overall, these dimensions are very small. You have to put a protective jacket here or protective coating, which is not directly involved in the mechanism of propagation, but it is there to prevent it from physical damage and to make it more versatile. Now, as I mentioned in my last slide, single mode and multi-mode. So this is how a single mode and multi-mode fibers, they behave and they look like. So if you see the single mode fiber, first of all, the core is very thin. This central green part is the core. So this core is very thin here. And in a multi-mode fiber, the core is thicker. So in a single mode fiber, you can, if you properly design your single mode fiber, then only one mode will propagate. That's why it is called a single mode fiber. And in a multi-mode fiber, you will have many more modes. So each one of these has their own advantages and drawbacks. Single mode fibers, they are used when you want to use high data bit rate for long distance communication because the dispersion is very small in those type of fibers. At least the multi-path dispersion is not present. Other types of dispersions are present. And in multi-mode, they are basically cheaper to operate because you can use a LED source here for a multi-mode fiber, whereas you need to use a laser only for a single mode fiber. So there are pros and cons of both of these. Now you have some optical fiber attributes, as I mentioned in the beginning, attenuation and then dispersion is also there. So both of these are very, very important from system design point of view. Whenever you want to design any system, so you have to look for attenuation and dispersion apart from bandwidth and signal to noise ratio. So these two are very important parameters. Attenuation is nothing but the reduction in the signal strength due to various losses. Say, for example, if you have an input pulse like this and it passes through an optical fiber, because of attenuation, it may decrease in the amplitude. So its amplitude has decreased, which is because of various type of losses. I will show on the one of the later slides what are the various types of losses. The relay scattering is one of the main factor. So if you see on the diagram at the bottom, you have a transmitter or a transmitter and you have a receiver on the other side, and then you have a optical fiber link. Now, as I said in one of the previous slides, that you can take this fiber to many kilometers, let us say 1,000 kilometers. It is practically possible to have it for so long distance. So obviously, because you are having a attenuation of 0.2 dB per kilometer, that is the lowest attenuation, you will need at some stage some amplification. So you can put some inline amplifiers as EDFAs or Raman amplifiers. So as to boost up the signal again. So in this bottom part, you see that this is the fiber attenuation. It is decreasing the signal strength. When the signal strength reduces below a certain level, you do not want it to go further down. You just put an amplifier, and the amplifier can again restore your signal with the amplification. Again, then the same thing repeats, and then you can put as many number of amplifiers as possible. However, you have a limit on signal to noise ratio. So ideally, I mean, you can put infinite number of amplifiers with infinite length, but practically your signal to noise ratio will keep on degrading. So that you have to keep in mind. But still, you can take this to a very long distance. So these are the three windows which I already mentioned. You have the first window which is 850 around 0.8 micrometer or 850 nanometer. Second window and the third window. These are the most important window which is centered at 1.55 micrometer. Second parameter, let me go back to this as I again mentioned here that this is for silica fibers. Different material may have different, I mean, such graphs, but silica is the most commonly used, and silica has a low attenuation at 1.55 micrometers. So that is why we always see such diagram in all the books. Second optical attribute, fiber attribute, which I mentioned is the dispersion. Now, dispersion is nothing but the broadening of the pulse. As you can see in this animation, you have some pulse input, and then it broadens as it travels along the length of the fiber. As I said, you have many kilometers of length. So the problem here is that suppose you have a digital signal with a very high data bit rate. It means high data bit rate means the separation between these two pulses is very, very small. So in that case, if such dispersion or such broadening of pulse is taking place, naturally they will spread and they will overlap each other, and then they will cause the inter-symbol interference. So that will limit your data rates. So dispersion is a very important parameter. Dispersion normally you measure in picosecond per nanometer per kilometer. Picosecond is a very small unit, 10 raised to power minus 12 seconds. So because it's a very small dispersion, but still it is significant if it is not controlled properly. So that's how I mentioned that if you have two consecutive pulses, then because of dispersion, they start to overlap. And ultimately your receiver, when it makes a decision whether it is a 1 or a 0, it will make an error here. Let's say at this point, instead of 0, it may take it as a 1. So your bit error rate, it may increase. It will definitely increase if these errors are there. So bit error rate is another very important parameter in optical fiber communication, and it directly depends on your dispersion. How dispersive is the fiber? So there are techniques to reduce this dispersion. There are new fibers which are having lower dispersion and all that. So given this attenuation, dispersion, then there are other some parameters like nonlinearity and some unwanted reflections. Ultimately, they all affect the performance of your optical fiber link from your transmitter to your receiver. This is the optical fiber link. And you see that if you have an input data waveform transmitted something like this, ultimately after many kilometers, you will start to see a degradation in the signal. This is the eye diagram actually. So you can see that now the signal is not so clean because lot of dispersion, lot of noise has been added because of various factors dispersion. So you need to actually take measures to avoid this. Otherwise, your bit error rate will increase beyond a limit which you do not want to happen. It will affect the performance of your system. So just a quick overview of what dispersion, what attenuation you can have. You can have absorption, you can have scattering, you can have bending, and then you have the subtypes of this. Scattering loss, this Rayleigh scattering is very, very important. Actually, if you increase the wavelength in this direction and your attenuation is shown here, then the Rayleigh scattering, you can plot it something like this. So actually this Rayleigh scattering is very significant here in the ultraviolet range, but not so significant in the infrared range. This is your you can say visible region. So actually this Rayleigh scattering, the loss due to Rayleigh scattering is proportional to 1 upon lambda raised to power 4. So that's why it decreases very quickly like this. It's a very important parameter. Dispersion and attenuation, as I said, two important parameters are there. So dispersion, you can have either multipath dispersion, which, as I said, it occurs in only multi-mode fibers. It is not present in single mode fibers. You can also have intramodal or chromatic dispersion. You call it as group velocity dispersion. This is present in all the fibers, whether it is SMF or it is MMF. This is present in all. And then you can have polarization mode dispersion also. This is also very interesting because you know what is polarization. Polarization is the that locus of the electric field vector as it propagates through the medium. So different polarizations may carry different signals, and then you have a dispersion. So this is further subclassified into material dispersion. Material dispersion is something which is because of the refractive index of the fiber being a function of wavelength or frequency. So n is actually a function of wavelength. So that's why this material dispersion is taking place. And waveguide dispersion is because of the geometry of the optical fiber. So we'll now discuss some system design considerations, that how your optical fiber system, what are the various considerations. Some we have of course already considered, attenuation and dispersion we have already seen. So actually all these optical fiber standards are governed by ITU, International Telecommunication Union. It's a very influential and big body in this. Just like IEEE is there, it is even more popular as far as these fibers are concerned. So G series of such recommendations that actually refers to transmission mediums and the transmission systems, digital systems, networks. So you have some G series given here, G.600 to 699 transmission media, optical system characteristics, and so on. G600 and 699, as I said, it is for optical system characteristics. So you have further classification of that. 600 to 609, you have the general recommendations, then 10 to 19 symmetrical cable pairs. This is actually the most significant for our purpose. 650 to 659, it gives the recommendation for optical fiber cables. And optical components, it is covered in this. And then optical systems like networks, optical networks, they are covered by this series of standards. For example, G.655, which actually falls in this range, it is the characteristics of a special type of fiber which is non-zero dispersion shifted single mode optical fiber. And it's a dispersion shifted fiber because you have some dispersion, zero dispersion at 1310 nanometer in silica fibers. So sometimes you do not want a zero dispersion because of some reasons. So you have a non-zero dispersion shifted fiber. Similarly, G.652 is the normal characteristics of a single mode optical fiber and cable. So when you see the system consideration, the system power budget is very important. System power budget, actually, just you know what is budget. Budget is something you make a statement of what is your input, what is the output, income and expenditure. So if you see, I'm not going into details because you will be studying this in detail in one of the later lectures. But briefly, I want to mention here that this power budget actually calculates that total losses which are available in this optical fiber. In the bottom part of this figure, you can see here. Just let me turn on the pen. Yeah, you can see here that this is the transmitter and this is on the other side, this is the receiver. So let us say your output power from the transmitter is plus 6 dBm, just an example. And the receiver sensitivity, that the minimum receiver power the receiver can receive or should receive, is minus 30 dBm. So if you take a difference of these two, plus 6 minus of minus 30 dBm, you have net 36 dB. So that is your budget, that you can afford to lose 36 dB along this length if you want a proper system, provided your output, the output, which is the input to this optical fiber, is plus 6 dBm. So there are various channel losses, which I am not going into detail right now, as this is just an overview of the optical system. So now you have important optical devices which are available. Of course, you know the sources, you have the detectors, you have the amplifiers, which are all very important for optical communication. I will just give you an overview of this so that we can quickly go to the next part, which is the research areas which are available to you. So as I mentioned earlier, erbium doped fiber amplifier, which you call in short as EDFA, it's a very popular fiber. You can see one module, actual picture of a fiber here, erbium doped fiber loop. This one is the fiber loop. So this is actually the amplifier. This is all the supporting circuitry. This is the input and this is the output. So EDFA can extend the transmission bandwidth or the distance of transmission to a significant extent. So you have a amplifier here shown by this yellow. You have an input signal and the pump laser. Actually, this pump signal is used to amplify this input signal. They pass through a coupler here and then they pass through this EDFA and then output is amplified signal. So that's why this is actually EDFA is called an inline amplifier. They are called inline amplifiers because you see that you don't actually realize that there is a fiber. It is the same, you can say fiber is going on from here and this EDFA also is in the form of a fiber. So that's an inline amplifier. That is the gain versus frequency characteristics of a EDFA. So this is taken from some simulation software, this snapshot. So you can see here that the gain of this amplifier is not 100% flat. Flat gain means when I say that if the gain is something like this, then I say it is flat gain. It means the gain of the fiber amplifier is not changing with respect to frequency. But in reality, this EDFA has a gain frequency characteristics, which is actually varying like this with the frequency. So there are some problems because of this, but there are also methods of reducing those problems. So even after, even though this is not a flat curve, EDFA is one of the most popular amplifiers used in optical systems. Optical sources, you have two main types of optical sources, light emitting diodes and laser diodes. And you can see, you know what is a laser is. Laser is light amplification by stimulated emission. So the properties of the laser source is that it has a very coherent and almost monochromatic output, very focused beam. You can have a very high power and very low diffraction beam. In this diagram at the bottom, if you see, yeah, here you can see in this diagram the characteristics of laser and LED. This LED is shown by this red graph. So power is low, but and also the bandwidth or the line width of laser is very large, which is not desirable in many applications. But yes, in many applications you are not bothered. And for example, in lighting and some low cost communication systems, it doesn't matter. So you can use LED, but laser, you see, it is a very focused and very small line width, which is actually a very good feature of laser. It gives you very small dispersion and very long length of optical communication. This is just a summary of the source characteristics, LEDs and lasers. The cost is low in case of LED, which is the main driving force for LED. It is very cheap as compared to the laser, because laser requires a lot of stabilization techniques and it's very expensive also. LED, this is another aspect of LEDs, that how to select a proper material for LEDs, because you know a lot of LEDs are there in the market nowadays, gallium phosphide and indium phosphide and lot of other material, third, fifth group compounds are available. So actually they are based on the fact that the material of LED should be a direct band gap semiconductor as shown here. Because there are a number of other materials which are having indirect band gap. I'm not going into details, just you can have a look at this diagram. What is direct band gap? That the conduction band and valence band, they are just one above each other as far as the momentum is concerned, this axis. Whereas in this, although the energy difference may be same, EG, but they are at different momentum, and then it requires much more effort to generate light in this. So in fact, one of the most unfortunate things the fiber optics has seen is that silicon is actually indirect material. This is indirect material, band gap material, because otherwise, you know, silicon is very widely used in your chip design and integrated circuits. But unfortunately, silicon is not a very good source of light, either absorber or generator. So, I mean, people are looking for many different materials. You see, gallium phosphide, gallium arsenide, indium phosphide. These are different materials which are actually used to generate light using LEDs. Now, I'm sure you must be aware, because particularly those students, because I understand there are faculty members also. The faculty members, they must be very well conversant, but students, they might be knowing that this wavelength is important. That actually determines the color of LED, and that depends on what is the band gap between the valence band and the conduction band. As here I mentioned EG. So this EG, that is the band gap. So when the electron falls from here to here, it generates some amount of energy, and that energy actually determines the color of light, whether it is yellow LED or blue or red. That depends on the material band gap. So this diagram actually gives you various materials, their various energy band gaps, their lattice constant. So all these are quite commonly researched materials for making LEDs. These are some popular band gaps of popular materials. Similarly, the detectors on the other side, you have a number of photo detectors possible. Uh, I mean, as far as the principle is concerned, you have mainly two types of them: pin photodiode and avalanche photodiode. But there are different types of materials. So they just do the, I mean, something opposite to what LED does. They take the light as the input, and then they convert this light into electrical signal. So that is the reverse process that has to be done at the receiver end. These are some popular materials for making this absorbers and photodetectors. Indium gallium arsenide phosphide is a very popular, very common material, because you can tune the band gap of this by changing the mole fraction of these materials, indium gallium, and then you can see there are lot many other. Now, by this time you might have got interested in that, how, because it is such a thin fiber. It's I said it is 9 micrometer in diameter, single mode, and 50 micrometer. It's still very small diameter. How actually optical fiber is fabricated? So optical fiber fabrication block diagram actually is shown here. Uh, this is a preform. This is a fiber preform core and cladding material. It is just like a rod of material, maybe double the thickness of a common pen which you are using. This, so it is having a diameter quite thick, but it is having the shape of core and cladding. I mean, the material inside this are core and cladding material. Then you put this preform into a drawing furnace. It's a very big furnace, a huge furnace. I will tell you, show you on the next slide. and then you apply some heat on this preform so that it melts, and then it takes the form of a fiber. It falls freely here. There are various control mechanism here. It looks very simple. Your diameter monitoring and temperature monitoring and flow rate monitoring, all these are there. Then there is coating, curing, oven, and then finally when this fiber is made, it is wound on a drum. So this preform something looks like this preform which I mentioned. And this drum, actually you see when you go to the market to buy optical fibers, they are available in this form. Even in your laboratories, you might have seen the spools of optical fibers. And as I mentioned, you have very big towers actually, which are used for fabrication of fibers. They are, I mean, many floors high towers. I mean, many stories of buildings are covered in this, and very expensive, very neat and clean room facilities are required for this. Even a small amount of moisture or small amount of impurity, any dust particle, it may render your whole fiber useless. So it is fabricated under very controlled conditions. So moving on further now, multiplexing in optical communication is again very important. Yeah, because you see that human nature is that it always needs more and more bandwidth. You might have realized yourself that as you get some bandwidth, soon I mean, start to realize that it is not sufficient. You need more and more bandwidth. In the very first slide, I showed you the same thing, that people are moving from 6 Mbps to now 100 Mbps is very common. And now our aim is to get Gbps, gigabits per second. So to achieve those, such high data rates, you have to go for multiplexing, because a single fiber, maybe it is having a huge bandwidth. Earlier when it was discovered, and even some years back, it was thought that the fiber has a infinite bandwidth. As for infinite in the sense that whatever we need, it has much more than that. But now it has been realized that even that infinite bandwidth is nothing in front of hunger of bandwidth of human beings. So now you had to look for some other ways of increasing the bandwidth further, and then multiplexing is one technique. TDM is time division multiplexing, then WDM is wavelength division multiplexing, a very popular technique here. SDM, as I mentioned, space division multiplexing, I will be discussing some more in the later part. This is how WDM looks like. The idea behind WDM is that you have the fiber, single fiber here, which is actually having very high bandwidth. But what you do is that you have here at the input n number of transmitters. Let me write it here, n number of transmitters, each having a different wavelength. Let's say this is at lambda 1, this is at lambda 2, and so on. This is at lambda n, and so on. So you have n number of wavelengths, and each wavelength is actually an independent channel which is carrying the data, independent data. And here you multiplex that data with the help of a multiplexer. And now that composite signal from all the wavelengths is actually passing through this fiber. Now it is mixed in time domain. You cannot differentiate this data in the time. It is all differentiable only in terms of wavelength or frequency. You can compare it with the time division multiplexing, where you allot different time slots to different signals. One time slot to one signal, second time slot to second, and third, so on in time division multiplexing. But here all wavelengths are mixed together, lambda 1, lambda 2, lambda 3, lambda n, but they are separable in terms of frequency or wavelength. At the receiver end, you have a demultiplexer, and you demultiplex it, and then it goes to the individual interfaces. So first WDM network use only 2 wavelengths, but now we are using 128 or even 256 wavelengths in a single fiber. So just let me tell you in very simple words. Earlier, whatever capacity of the fiber we had, let us say there was one fiber point to point link. Now when I have 256 channels, it is equivalent to saying that the same fiber is carrying data equivalent to 256 fibers. So you see how much tremendous bandwidth and data rate this fiber is able to take. Now I will move to the future developments, possible research directions in optical communication and networks. So if you see when the light is propagating through the optical fiber, there are some physical dimensions which you can play with and which you can optimize so that your bandwidth or capacity is further increased. One of them is, in fact, two of them, but I write them together, amplitude as well as phase. So you can change the amplitude of the signal and you can also change the phase of the signal. You see here, this is a QAM signal. So you have amplitude as well as phase. Second is polarization. You can have either Y polarization or X polarization. So this gives you another degree of freedom that you have got two polarizations here. So remember in RF, we do not have, much dependence on polarization. So here, but in optical, it is very important and you can have polarization dependence also. Wavelength is of course very important. And then space division multiplexing, which I will take on. So optical modulation and detection technologies, you can research or you can work in various different types of modulation techniques. Three of them are shown here: IMDD, that is intensity modulation direct detection. In this case, DD is for direct detection and IM is for intensity modulation, where you simply demodulate and modulate the optical signal as per the amplitude of that. That is the intensity of that signal. DPSK is that where you modulate the phase and maybe amplitude also together. So binary phase shift keying or quadrature phase shift keying. And then you have another dimension added, that is the coherent modulation and detection. Here you can have this polarization division multiplexing and combined with the QPSK and QAM. So you have lot more bandwidth available and lot more research areas to work into this. Now, as I mentioned in the very first few slides, space division multiplexing is the next technology which is going to be very popular now. It is already very popular. A lot of research is being done. So what is space division multiplexing? You have a fiber like this. Here you can see this is the fiber, and it is actually multi-core fiber. It means the same fiber is having multiple cores. So each core can be taken as a different, you can say, effectively a different fiber. So if I say I have n number of cores here in a single fiber, it means equivalent to saying that these are n different optical fibers together. And this is possible because of the advancements in digital signal processing on both the transmitter and receiver side. Similarly, you might be knowing that earlier people moved from multi-mode to single mode fibers. But now again, there is some interest in again multi-mode fibers. Although here the number of modes we are talking is not too much. We call it as a few modes fiber. So you are talking of only a few modes which can be easily separated by using the DSP on this side and the DSP on this side. You can call it as a MIMO, multiple input and multiple output. So this is a space division multiplexing. So this is becoming very popular. I will now quickly try to wind it up with a few more slides. Future development and possible research directions. The 3M technologies, as I already mentioned, this multi-level modulation format. You can have 16 QAM or 64 QAM. New optical fiber technologies, multi-core fibers and multi-mode control fibers, MIMO. So these are 3M technologies which are very popular. Quadrature amplitude modulation is a coherent transmission. It is seen as a possible successor of today's 10G technology. Mode division multiplexing, in fact, I have already covered. All optical communication networks. In the very beginning, I mentioned that still it is still a far reality, because you whatever networks you have today, they are still a mix of optical and electrical components or electronic components. So the dream of all optical researchers is that if you have all optical networks, all signals will be processed in the optical domain without any form of electrical manipulation. So it will remove the bottleneck of electronics and it will give you further higher speeds. Intelligent optical transmission networks. Now you know that in every field of science and technology, machine learning and artificial intelligence, they are coming. So photonics and optical communication is also not untouched by machine learning and artificial intelligence. So you can do, intelligent bandwidth allocation and switching and routing by depending on what is the quality of service that you need, or depending on what is the available bandwidth. So you can do that switching. Laser technology on the one side and also photo detectors on the other side. A lot of scope is there. You are coming with new lasers every day. Research is going on. How to stabilize the laser source, how to reduce the line weight. All these factors are there, and that is another area of research if you are interested in working in the device level, because there might be two different domains. One is if you are working in the device domain, other is you may want to work in the communication system domain. So the earlier applications I mentioned, the modulation formats, etc., they are from the system point of view, whereas this is at the device level. Similarly, laser neural nodes is another possibility. Optical fibers itself, you are having a lot of scope. You can research on the optical fiber profiles and their materials, their doping, how to reduce the losses and other impurities further. Photonic switching, because when you are talking of optical networks, switching will be very much an essential part of it. So novel high-speed devices based on photonic crystals, functional materials, MEMS, you can do research in that. Optical amplification, as I said, EDFA was one of the biggest inventions in this domain. So you can further improve, you can have gain equalization, gain flattening, or maybe you can have some other materials, Raman amplifiers, not only EDFA, but Raman amplifiers, thulium doped fiber amplifiers, that is called EDFA. Or you can have a hybrid of these, EDFA combined with Raman, and how the spectrum is changing in that case. That is another area of research. Transmitter receiver technology, I already mentioned. A lot of LEDs are coming now. New LEDs are coming. So you can work on those LEDs. Your main aim is that how to reduce the signal to noise ratio. Another very important area which is emerging is energy efficient optical networks. Now, although it looks like that optical networks, all these your routers and modems, they do not take much power, and that is true also. But the thing is that if you see it in that perspective, that you are using huge number of such devices now, huge number, and their total power is actually now a serious concern for researchers. Their CO2 emission and whatever energy they are taking, it is a serious concern already for the researchers. So energy efficient networks, or you call them as green networks. That's a very popular word, green network. So you have again a lot of scope here. All on the all sides, you see remote monitoring, renewable energy, efficient access network. So all these things you can actually work on. Another very popular research direction, which is gaining a lot of importance, is free space optical communication or optical wireless. Optical wireless. Yeah, so you can see that the places where you cannot lay a fiber, it is difficult or it is time consuming and costly, because it may be difficult to lay a fiber from this building to this building. So what you can do is you can have a transmitter here, a receiver here on the other side, and then they are, communicating in free space. Of course, it is a line of sight communication, LOS, and here also a lot of scope of research is there. As you can see from this slide, optical wireless communication, you can have either indoor system. You must be familiar with the visible light communication and all those things, visible light communication, internet, indoor internet using Li-Fi. So all those are actually research areas, and outdoor, of course, terrestrial links, space links, deep space links. Shown on the next slide, you can see this is a free space optical network connecting data center and ships and satellites and submarines and various sensors. And this is a indoor communication using Li-Fi. So all devices are actually connected through internet using uh, that light communication. Of course, you are familiar with the lighting. LED lighting is now very popular. So as I said, one of the areas of research is how to do research in LED, is how to increase their quantum efficiencies, which different materials work. And then fiber optics is also directly used in illumination. You see, this is made of fiber optics only. So these are some examples. Solar cells is a very important area nowadays. You know, India has plenty of sunlight. A lot of rooftop solar panels you might have seen nowadays. So it is again a very interesting area. Specialty fibers. Now there are two things. One is that photonic crystal fibers are very important. You can see that this is a usual fiber, and then in that usual fiber you have either some air holes or some other material going through this. So basically it has got two you can say aspects. One is if you can use it in communication, because in communication these photonic crystal fibers have lot of capability of tuning their dispersion and other characteristics. You can change their distance of the two holes, you can change their diameter, you can change the material. So you can actually change their parameters quite flexibly. So you can have much more flexibility. Another aspect of photonic crystal fibers is in fiber sensors. Very important application. You can see here this liquid is filled here, or maybe somewhere here there is an analyte here at the bottom. So what you can do is these hollow air holes which are there, you can fill some liquid or some analyte, and then see how it changes the property of propagation, and you can detect using this some very important medical conditions or chemical properties of this. So that is a summary of the application areas. Some of which I have given overview: high-speed communication, optical networks, devices, solar lighting, and solar cells. And then there is no limit. This dot means it's just limited by your imagination. Biophotonics, Spectroscopy is very popular in material science nowadays. Optical and computing memories. Optical computing is also coming. Imaging, industry, sensing. Sensing has got many applications in optical fibers. Fiber break grating sensors and all that. So no doubt the market of global optical communication and networking, it is zooming like anything. So you see the annual growth rate, it is continuously increasing. And yeah, so there is a phenomenal progress in every aspect of OFC. The future belongs to optical fibers. Yeah, so that's all from my side. Thank you.
Okay, so thank you, sir, for giving very informative lecture on the overview of optical communication, and I think it will definitely help the participants who are not from the optical communication background. So, any queries from the participant side? Yes, participants, please. Yes. Yes, you are audible.
Thank you, sir.
So the question is, I cannot hear properly.
Your voice is breaking. Can you just type in the chat box?
Hello, sir. Good afternoon.
Good afternoon.
Yes, sir. Myself Jayesh Prajapati. Sir, I am working in the area of radio over fiber. That is some sort of a combination of optical as well as the wireless communication and all.
Yeah.
So I just try to combine both that particular domain as a, and then after I have just used the different level of QM level, and just I have developed a link using OFDM higher order modulation scheme and all. So sir, where I have gone up to approximately 2 to 3,000 kilometer, up to which I am getting some sufficient. Sir, one my basic question is that normally at the receiver side we are just measuring some BER, or let us say Q factor and all. So whenever we are working on the simulators and all, they are giving some values like BER value, or that is in terms of 10 is to minus 99 or something. So is it actually, sir, practical
No, no.
values, or?
Yeah, it's a very good question actually, because those students or researchers who are doing simulations,
Yes, sir.
it's actually they have to look into from the practical point of view also, because see what happens in a software. I always tell my students that if you give anything, any input, it will give you some output. Even if you give junk input, it will give you junk output. But
Yes, sir.
based on your experience and based on your, common sense, that should not be taken as it is. You have
Yes,
to properly see the interpretation of results. 10 to the power minus 99 is, I don't think it has got any relevance.
yes, sir.
So basically, maybe what you have to do is that you can start with some practical values, and then later on you can modify your system or whatever research you are doing, and
Yes,
try to see that where you are going from 10 to the power minus 9 to maybe you are going to 10 to the power minus 10 or something. But yeah, you are right that 10 to the power minus 99 or even minus 30, they have got no practical significance. It's
yes,
only
because sir, normally sir, 10 is to minus 9 to 10 is to minus 10. That is approximately somewhat reasonable value. But
Mhm.
maybe the limitation, or what we can say, that due to the ignorance of few of the parameters while designing these type of things and all. So
Yeah,
practically,
yeah, yeah.
yes,
Yeah,
yes.
so you have to, yeah, I mean, look it from a practical perspective.
Okay. Thank you very much, sir. Thank you.
One question is how to do efficient optical image compression and encryption techniques for secure transmission in optical networks. So implementation point of view, please guide regarding labs available in India. That is, sorry. They are two different.
Yeah, you mean to say image compression using optical?
Image compression and encryption techniques for secure transmission in optical networks. How to do efficient optical image compression? That is question by Savita.
Well, actually, I have not worked directly in this area. So you can maybe throw some more light at how you are doing it right now.
Hello.
Hello.
Sir, can you please, may I audible?
Yeah, you are audible.
Sir, can you please tell me the role of optical fiber in the plasmonics or the LSPR or the SPR techniques?
Yeah, directly fiber has as such hardly the role, but yeah, fiber optics, not fiber optics, but photonic devices, they have this role because plasmonics, I think you are using for sensing and all those applications.
No, sir, I'm asking about this plasmonics sensor based on optical fiber. Design using optical fiber.
Yeah. I mean, you are not talking about the communication aspect. You are talking about at the device level.
Yes.
So, I mean, there are a lot of variety of fibers available. Maybe you can, deposit some cladding based on the analytes, and maybe you can remove some part of the cladding, and you have the evanescent field. So, I think that is the mainly the principle which is used in optical sensing. If you are using it using optical fiber. So whatever evanescent field is there, you can sense it, you can put some analyte there, and then it will behave according to the properties of the analyte. So you can do a lot of interesting things here. And you have intrinsic as well as extrinsic sensors. So maybe directly you are modifying the optical fiber, or maybe you are having some other sensor and fiber optics is just used to carry that signal.
So do you have any particular idea about LSPR sensor using optical fiber?
LSPR?
Actually, I'm in the initial phase, so I want a little bit.
LSPR, can you elaborate? What is LSPR?
Localized surface plasmonic resonance optical sensors.
What exactly? Because the principle I told you that it is the same principle in all plasmonics, that either you use the evanescent field, basically.
Okay. Thank you, sir.
Okay.
Okay, so I think.
Good afternoon.
Yes, please.
Sir, actually, I have one more question, sir. Sir, actually, can you put some light? Actually, I want to start my work in the direction of visible light communication, sir. I have gone through some papers, but regarding practical aspects, implementation or lab hardware part, where actually I can start up, because I want to do some practical work in designing of VLC link. But from where I should take the beginning part, because I am aware about the basic concepts and theory, and I have gone through some research papers. But regarding hardware, to design the links for the visible light, like optical, kind of a optical wireless communication, I want to work upon.
Maybe the beginning point may be that you can maybe start a small project, and you can use some those Raspberry Pi and all those kits. Okay. And then you can have a small setup initially. I mean, back to back, you have a transmitter and then you have a receiver. So maybe you can start with that, and then later on you can find out that which labs. Most of the IITs, IIT Delhi they have a strong group on this free space optical communication. Many other IITs, many places you will find the facilities in the lab.
Okay.
Hello.
Yeah.
Sir, one more question. Sir, in the sensors, optical based, especially in the plasmonic sensor, this wavelength will be reduced at the the output point. So, due to this loss of light. So, is there any exact reason behind this? Because most of the sensors are in the IR or the near IR region at the output. And at the input, we are providing either 1310 or the 1550. So this wavelength will be reducing. So can you tell me the reason behind this or something?
No, why it will reduce?
So because we are in the plasmonics, we are remove the cladding, na. So light will be some waves will be
No, but
losing.
wavelength will not reduce. You said wavelength will be reducing. Why wavelength should reduce? It will be the intensity which will be reduced.
Okay, wavelength is constant, only intensity is reduced, right?
Yeah, I mean, until unless you have some mode change. I mean, if
Okay.
you're removing the cladding and then you are having some new modes generated or some new modes lost, there is why it should change. I mean, just by removing the cladding, I don't think the wavelength will change. It will be the
Okay,
intensity
only.
which will be changing. Yeah, until unless you have some new modes coming.
Okay. Thank you, sir. Thank you.
Okay, so I think we should continue these questions in the next session. So basically, we have the next session that is again by Professor Vijay Janyani, and that is from 2:30. Okay, so I think we should have break right now, and then you can ask, or we will start from the another session that is gigabit passive optical networks. Okay, so you can ask some questions there also. So you all are requested to join the next session that is from 2:30 on the same link. Yes.
Okay. Thank you.
Okay, sure, sir. Thank you.